Yo, calculus students. I made some mistakes on this homework. Um, I'm going to make sure you have the right questions before you get started. Now, some of them, the questions are bad. Some of them, the copies, like when I made a PDF version, it didn't come out. First thing you got to notice is that this thing is a 12. In your homework that you picked up, this copy, you have a 1. So that's bad. It'll be a lot easier to do now. The next thing is this. It just doesn't work out well when it's x to the fourth plus minus 4. So please change it to x squared plus 4x. X squared plus 4x, not x to the fourth minus 4. Honestly, this question stinks, but whatever. Here, it has x squared plus 2. We don't want x squared plus 2. We want just x minus 2. It makes it a lot easier. Everything else is good. Okay? We're talking about continuity here. When are functions continuous? Well, functions are usually continuous everywhere. The question is when are they not continuous? That's really what we're going to figure out. And easiest way to go about this is hey, you're not allowed to divide by 0. That's the first thing you should always check. It's do you have a denominator? Could your denominator ever equal 0? Second thing is okay, is it a special type of function that could jump, a special jump function? Okay, or is it a piecewise function? Okay, piecewise functions possibly have jumps. And that's really what we're focusing on. And then we have these pointwise functions, which we'll talk about later. But denominator is equal to 0, and then heads up for jumps. We'll go from there. Cool. So for evaluating continuity, we want to see when is the function potentially undefined. Now, I'm just going to factor everything to start off with, just because once we have everything factored, we can kind of really evaluate what's going on at certain x values. Now, don't jump ahead and start canceling things out. We need to figure out the x values when the denominator equals 0. Well, when x is 6 and when x is negative 2, this is when the denominator equals 0. I know you want to cancel the x plus 2's. Don't do it yet, okay? I'm not even going to do it at all. I'm going to say that's part of my function. So don't do it at all. We will look into canceling things later. All right. Now we got to figure out the type of discontinuity. We can't just say this is my answer. These are when the function is discontinuous. It is true. But we want to know the type. Okay? Reminder. Holes, when you end up with a 0 over 0, and you could think about plugging in values close to what we're plugging in, that would get values close to 0, and those zeros would cancel, and you'd end up with numbers that you can divide, and you'd get a value. 0 over 0 holes. Holes are removable. Okay? Numbers over 0 where the 0 doesn't go away, and we'll talk more about these next class. Numbers over 0, vertical asymptotes. We will really get into that more next class. Right now, we're just going to call it a vertical asymptote, or it's a non-removable infinite. All right, so I'm going to go ahead and plug in 6 into my original function and see what I get. I get 6 times 8 over 0 times 8. Okay, it's the 8's cancel, but that 0 is still there. The 0 can't be removed. The 0 is non-removable. So 0 in the denominator, number in the numerator, non-removable. You say x equals 6 is a non-removable infinite discontinuity. X equals negative 2. Okay, well, if I plugged in negative 2, I'd get negative 2 times 0 over negative 8 times 0. Now, you're not allowed to have 0 over 0. That's undefined. So yes, this is a discontinuity because you have 0 over 0. Your denominator will have a 0. But this is when we think about last class and we talked about finding the limit as x approaches negative 2. If I plugged values in negative 2.001 and negative 1.9999, what you would end up having is like very, very small values that were approaching zero, that were really close to zero. And those very small values, that very small value in the top and the very small value in the bottom would be the same very small value because of the factor, okay? Which means it would be able to cancel. So we can essentially think about canceling the zero. We can see we're going to be approaching a specific location. We have a limit. We don't have a function value. That's a hole, okay? So -2, because the zeros can be removed, is removable. The location is -2, comma, -2 over -8, which is positive 1/4. Got it? Now we're going to go a little faster because this video will take forever unless I go fast. Shout out Miss Salas. What up? Okay. Factor out 2. Factor out x. Factor top. I don't care when the top equals 0. Factor bottom. I do care when the bottom is 0. The bottom is 0. Don't cancel anything. X equals 0. Because if I plug in 0, 0 times anything, 0. If this was another value, if this was like 5, it would not be a discontinuity. Oh, come on, get out of here. It was tapped on. -3. 3. If I plugged in 0, I get 2 times 3 times 2 over 0 times 3 times -3. Okay, 0 is not going to cancel with another 0. Boom, non-removable, infinite at 0. These are my discontinuities. X equals -3. Okay, so I got 2 times 0 times -1. I'd get -3 times 0 times -6. Okay, the zeros do cancel, which means they're removed. This is the idea of like, we have a hole, we are going to be able to approach it, we'll have a location, but we won't have a function value because we can't divide by 0. I get -2 over positive 18, so that's 1/9. I'm sure you can't see that. And now 3, 2 times 6 times 5 over 3 times 6 times 0. The 0 will not be able to cancel. This is a number divided by 0. This is another non-removable infinite. We have 3 discontinuities. We have labeled them. We are good. Next, H. Let's go ahead and just start by factoring. Cool. Set the denominator equal to 0. Pump the brakes. Don't cancel yet. Whenever we have a 0 in the denominator, we have a discontinuity. X equals 0 is a discontinuity. It would make the entire denominator 0. X equals -4 is a discontinuity. I'd get 0 over 0. Now, so we don't have a function value. However, plugging in these values would help reveal what's going on. Whoa, this is crazy. If I plug in 0, I get 0 times 4 over 0 times 4. Zeros would cancel. 1 over 1. 4 over 4 is 1. Think about this. You'd have a very small value close to 0. You'd have a very small value close to 0. They are 1. You have something close to 4 divided by something close to 4. That's 1. Boom. You have a removable discontinuity and its location is 0, 1. Cool. Let's check -4. 4 times -4. -4 plus 4. -4. -4 plus 4. The zeros cancel. They're removed. This is also removable. Holy cow. You can have 2 holes, no asymptotes. Of course you can. You can have whatever we want. We can create whatever we want. The discontinuity's location is at -4. -4 is the location. Its y coordinate would be approaching those zeros essentially canceling positive 4. How did I do it up here? I liked it up here. Oh, okay, yeah. I kind of did it in black. It is nicer when you change colors. Removable. 0, 1. Negative 4, 4. I'm going to graph this because it's fun to see our handiwork. You guys obviously don't care about any of this. You're like, can we just go to the next question? This is stupid, Mr. Messner. I just want to get the right answers. Yeah, look at that. It looks like just a straight line. Yeah, it's a straight line at 4, because think about it. Cancel, 4. So why did I say it was 0, 1? It should be 0, 4. Oh, because the 4 is still there. Yo. I was wrong. It's 4 times 0 times 4 over 0 times 4. Or the x's cancel, the x plus 4's cancel. You are just left with 4. This is why I do this. This is why I check this. It's a good one. I haven't done one like that. Cool. All right. Now, denominator equals 0. This is very much a, just like, do you really remember the unit circle, or are you just pretending? When does cosine equal a half? That's when an adjacent's a half. The adjacent's a half at pi over 3 and 5 pi over 3. Okay. If I plugged in pi over 3 and 5 pi over 3, I'd get 0. I would not get 0 in the top, which is why these are both non-removable. Infinite. Okay. Next one. X plus 11, x minus 2. That works. X minus 2. When does the bottom equal 0? X equals 2. If you plugged in 2, you'd get 13 times 0 over 0. If the zeros cancel, you get 2 comma 13. So this is removable. The location is 2 comma 13. When the zeros cancel, you get a 1. Oh, there's so many different ways to factor this. And what's important to you guys is, like, if you have a way, go with it. If you don't have a way, they're going to be easy enough to figure out. Okay? And I'm going to show you what that means, because I don't want to go through, like, the technique to factor. I'm just going to, like, figure it out. I know that 2 things times 2 things are going to be these 3 things. As long as this is a version of x, this is a version of x, I'll have x squareds. A number times a number will get a number, and then when I distribute, I'll have an amount of x's. Now, I don't just have x squared, I have 2x squared. So I know this is 2x plus something, and then x plus something. I know the last 2 numbers have to multiply to get negative 15, okay? But I got to add our amounts of x's to get negative 7. I already kind of know what's going on, because I know that if I have negative 5 here, I'd get negative 10x. And if I have 3 here, I'd get positive 3x's. Negative 10x's, positive 3x's. Boom, I figured it out. If you don't remember that, there are other techniques. The other techniques involving always doing like a number puzzle where you're not looking at 2 numbers multiplied to get negative 15. You're looking at 2 numbers multiplied to get negative 30, which is a times c, and then adding to get negative 7. You then like rewrite, and you either factor by grouping or you use a box. But whatever, I'm just going to figure it out. You guys do whatever technique you want to do. Again, this has got to be 2x and x to get 2x squared. This has got to be a version of 3 and 1. I got to get positive 1 x's in the middle. So I want 3 x's and negative 1 x's to get negative 2 x's. 3 x's, negative 2 x's, give me 1x. Anyways, boom, we got it. When does 2x plus 3 equal 0? You have to solve that. Subtract 3 divided by 2. x minus 1 equaling 0, x equals 1. Those are our two discontinuities. Don't cancel things too quickly. Oh, this will be fun, though. If I plug in negative 3/2, I get 0 over 0. I'm going to turn it into negative 1 1/2. This is negative 6 1/2. This is negative 2 1/2. I can't figure that out, so I'm going to use fractions. We get 0 over 0. I get negative 3/2 plus negative 10/2, which is negative 13/2. It's times. I got 0 and then negative 3/2, negative 2/2, which is negative 5/2. If I divide it, it's the same as multiplying by the reciprocal. 2's cancel. I get 13/5. Good arithmetic practice, but probably not something you're doing on your quiz. Probably keeping it simple on your quiz. If I plug in 1, I'd get 5 times 4 over 3. Sorry, 5 times 0. The zeros won't cancel. So again, this is a removable. This is location. It's a whole. This is a non-removable infinite. Sweet. To the point-wise, before we do the point-wise, let's go to the special jump function. If we are looking to the left of 4, we keep this as positive x minus 4, but this should be a negative x minus 4. We would end up getting a negative 1 value. If we look to the right of 4, we would have the positive x minus 4. We would have the positive x minus 4. We get 1. This is not a removable discontinuity. This is a situation where we have a jump. This is the special jump function. You need to be familiar with this being the special jump function. Okay, it jumps from negative 1 to 1. Now let's go to this other pointwise function because it's going to take a little bit longer to analyze. This is a pointwise. Pointwise being like, yo, we are using a piece for pretty much everywhere, except at 2 locations we got points. We got a point here, we got a point here. Okay. Here's how we handle the pointwise. Just like we were doing the previous examples. Okay, just like we did the previous examples, let's just analyze the dominating piece. So I'm just going to go ahead and ignore this for now, and I'm just going to talk about this guy. Cool. I'll set the denominator equal to 0, pump the brakes, don't start canceling. Set the denominator equal to 0. I'm going to just analyze this. I get x equals 2 as a discontinuity. If I plugged in 2, I'd get 1 over 0 times 1. 0 does not go away. It does not cancel. If I plugged in 2, I'd get a number over 0. The 0 will not be removed. This is non-removable. This is an infinite. The big piece has asymptote. If I plugged in 1, I would get 0 over negative 1 times 0. Now, the zeros will think about canceling the zeros, and what are you left with? 1 over negative 1. So that means we are removable, and the location is 1 comma negative 1. Okay, I've done some analysis. If the question was analyze this function's continuity, you would say you have a discontinuity at 2. It's a non-removable infinite. And you'd have a discontinuity at 1. It's removable. It's a whole. Here's the location of the whole. And you'd be done. But this is different because we are told, hey, actually, you're not supposed to be using this guy at 1. You're supposed to be using negative 1 at 1. This is a point. Well, hold on. At negative 1, at 1, I'm putting a point at negative 1. So it's like at 1, I'm putting a point at negative 1. I know this has a hole at 1, -1. Here is a point at 1, -1. Guess what happens? The point fills in whatever this looks like's hole. So we had a hole, but the point fills it in. No longer is this a removable discontinuity. This discontinuity just got removed by the point. Okay? That means it's not a discontinuity anymore. We're good. Okay, cool. Well, at 2, I'm not supposed to be using this function. I'm supposed to be using -1/4. Well, I was told that at 2, this original dominating piece has a non-removable infinite. Well, there it is right there. At 2, we have an infinite discontinuity. It can't be removed. Even if there's a point somewhere, like 2, -1/4, we're not going to be continuous. What that means is, like, after all of our analysis, we will still keep non-removable discontinuities as non-removable. They are still discontinuities. We had a removable discontinuity that got removed by the point. Pretty cool, but confusing for a lot of students. We'll see more of those later. Next type of question. Find a value to ensure the function is continuous, okay? Now, we haven't looked at piecewise functions and if we're continuous yet. We'd go straight into these, which is fun, but like probably would have included a different example where it's like, hey, if f of x is, let's just say, x squared minus 2 and x plus 3, and this was x greater than -1, sorry, it should be less than, but whatever, x less than -1 and x greater than or equal to -1. Examine the continuity. Well, this is a piecewise function. We could possibly jump, but we don't know if we jump or not. We have to determine, like, yo, where does this one leave? Where does this one pick up? At -1, which is the important point, where does this one end? Or what is the limit as x approaches -1 from the left? If I go to the left of -1, that's like -1.001. I'm plugging in that into here. If I plug in -1 in there, I get -1. Such bad numbers. So if I plug in something close to it, I'd also get -1. If I plug in -1 into the second piece, like if I plug in -0.99999, well, plugging in -1 into that gives me 2. Plugging in something close to that would give me 2. What we have is, like, we got this x squared, which will stop here, and then we got this x plus 3, which picks up from there. That's a jump. We have a non-removable jump at x equals -1. What do we pay attention to? The fact that we're going to leave one and pick up another at a specific x value. So that's what we're going to pay attention to, with one exception is, like, we want to ensure that the function is continuous, okay? So we are asked to find a to make sure the function is continuous. Well, if the function is continuous, that means if I look to the left of -1 where I leave 1, it needs to equal what I get when I look to the right of -1, which will actually be this piece. Okay? So, if I plug in -1.00001, I'd plug it into this piece. If I plug it into that piece, it's like plugging in -1 into that piece. I get -a plus 3. I'll do the same thing here. I'd plug in -0.9999. What I get is something very, very close to the value when I get when I plug in -1. Like, plug in -1. If you plug in something close to -1, you'll get something close to that value. So plugging in -1 here, I get a minus 2. To ensure that the function is continuous, we got to make sure they meet up. We got to make sure the limit exists. The left-hand limit equals the right-hand limit. So I'm just going to solve this. Add a, divide by 2. Don't divide by 5. That's silly. Cool. Next, 3 pieces. This piece used up until 1. Then from 1 to 3, this piece is used. And then from 3 on, that piece is used. To ensure the function is continuous, I gotta drop off my black piece to the left of 1 at the same spot where I pick up the middle piece at 1 to the right of 1. And then the middle piece to the left of 3 needs to pick up with the bottom piece to the right of 3. Okay, it's just like the last lesson that we did. Just looks different. So here we go. I'll get 2 equals a plus b. Here, I get 3a plus b. Again, I'm plugging these in for x, not for a. A is a value that we're trying to find. And that'll equal 0. Nice. What do we do now? Well, we have a system of equations, 2 equations, 2 unknowns. Quick little review of systems of equations. We like to solve for a variable, any variable that you'd like to, and substitute it into the other one to eliminate that variable. I'm solving for b because I just see 1b right here. I'm going to take b, substitute it into this equation, and I'll get 3a plus 2 minus a equals 0. And that's 2a plus 2 equals 0. That's going to be a equals negative 1. Once I get a, plug that in, we'll find b. Plug that in, we'll find b. 2 minus negative 1, b is 3. Okay, so negative 1 is a, b is 3. Okay, more of the same. Here, to the left of 0, we need to make sure that equals to the right of 0 so we don't jump. We did this last class often, so it shouldn't be crazy. To the left of 0, I'm plugging in something close to 0 here. It's just like plugging in 0 what I'd get close to. Cosine of 0 is 1 plus a. If I'm to the right of 0, I'd be plugging it into x minus 4a. So I would get 0 minus 4a. I get 1 equals negative 5a. A equals negative 1/5. Good? I'm going to skip showing the limit notation. I'm just going to kind of do it easier. Now, when we get into the second semester, if we want to show things are continuous, you actually have to do all the work with the limit notation, but it's not the second semester yet. So we'll just go with this and just say, okay, the top and the middle need to meet up at 1. The middle and the bottom need to meet up at 2. A equals 2 plus b. 4 plus b equals 2b plus 1. Oh, cool. All right, well, I can find b, and then I can find a. 3 equals b. A equals 5. If you need help getting that, do the math. Cool, a couple more. Skipping the limit notation. We got to make sure the top piece meets up with the bottom piece at 2. 4 minus 3a equals 8 minus a. Negative 4 equals 3a. 2a. Add 3a, I get 2a. This is where I rush and I'm going to make mistakes. 4 minus 3a, 8 minus a. Minus 4a equals 4. a equals negative 1. No, I screwed up. Add a minus 2a. If you're like me and you're screwing up, slow down. I should be slowing down. Cool, negative exponents. You guys know what a negative exponent is? Oh, man. My pre-calculus kids don't. Top needs to meet up with the middle at negative 1. Limit as x approaches negative 1 to the left. Limit as x approaches negative 1 to the right. Get 4 times 2 to the negative first power. Think about a positive power. What does that mean? Multiply. Yo, what's a negative power mean? Divide. Divide by 2 3 times. Or it's the same as 1 over 2 cubed. Positive powers multiply. Negative powers actually mean divide. It's pretty cool how that works out like that. This is negative a plus 2b. I didn't give you much space for this. Two equals negative a plus 2b. The middle piece needs to meet up with the bottom piece at 2. 2a plus 2b equals 3 squared, which is 9 minus 2, which is 7. This is so gross. But whatever. I can solve for a. I got 11/6. I should have put 0. If I put 0, it would have been nicer. If b is 11/6, what's a? 11/3 minus 2. That's 2 times 11/6. 2 times 11/6. You can divide the top and bottom by 2. You get 11/3, or the 2 cancels with the 6, makes a 1 over 3. That's 6/3. 11/3 minus 6/3 is 5/3. Okay, so that's A. That's B. Okay. Point-wise, this guy is dominating. Let's evaluate its continuity. Well, it's x plus 2 times x minus 2 over x minus 2. X equals 2 is removable, because when I plug in 2, I'd get 4 times 0 over 0. The location of the removable is 2, 4. That top piece has a hole at 2, 4. To make this entire function continuous, fill in the hole. This has to be equal to 4 when x is 2. I plug in 2. This has to equal 4. B has to be negative 2. Think about it again. Holes can be removed with very expertly located points. And once you remove, you're good. Next one. Focusing on the dominating function. X plus 2, x plus 3, x plus 3. Okay. X equals negative 3. Removable, because I would get negative 1 times 0 over 0. Boom, boom, gone, giving me a location, negative 3, negative 1. Okay? Negative 3, negative 1 is a location of a hole. To make sure the function is continuous, this piece at negative 3 needs to fill in the hole, which means this piece at negative 3 must equal the hole's location, negative 1. I have a hole at -3, -1, fill in the hole, makes the function continuous. Add 3, divide by a negative. Cool. What is the intermediate value theorem? Well, if you're in my 7th period class, I hope you're paying attention now because you guys fell apart very quickly. We might have to change things for period 7. I seriously think I'm going to teach the lesson first. And then you guys finish up with the quiz. B-Lunch is cramping my style with you guys. But here's what you were going to learn. Yo, if you got a function and your function is continuous, and that's what today is all about, continuity. If your function is continuous, and you know 2 points on that function, say 1 point here, 1 point here. That's all you know. Function's continuous, and here are 2 points. The intermediate value theorem says you are guaranteed to cross through all of the y values in between these 2 y values. For example, if this was like 5 and this is -1, I could say, hey, I bet you f of x equals pi somewhere. Yeah, of course. It's like, well, pi, 3.14, is somewhere between -1 and 5. These 2 points, I don't know how they're connected, but they have to be connected. I'm going to have some x coordinate that will produce the y value 5. I'll be able to solve that equation. Intermediate value theorem is all about the existence of solutions. Okay? So, you want to show that this function equals 4 for some x between 0 and 3. Now, this is important. These are x's. All you need to do is find the 2 points. Plug in 0, I get 2. Plug in 3. 27 minus 9 is 18, plus 3 is 21, minus 2 is 19. Yep. There is an x between 0 and 3 where, plugging that x into the function, I'll get 4. Why? This function is continuous. Why is it continuous? It's got no denominator. Since it doesn't have a denominator, I can plug in any x value, boom. Since I have the point 0, 2 and 3, 19, I will cross through 4 somewhere, and there's going to be an x value that will produce that y value 4. That's it. Root is another word of saying 0. The root's between 2 and 3. Sure, these are x's. If I plugged in 2, 8 minus 12 plus 3. If I plugged in 3, this is -4 plus 3 is -1. If I plugged in 3, 27 minus 27 plus 3 is 3. Boom. There's got to be an x between 2 and 3 such that plugging x into my function gives me a y value 0. Somewhere between 2 and 3. Since I go from -1 to 3, I'll have to cross through 0. I don't love this one because I don't give you an interval, but it says, like, show that this equals pi. Well, like, all I need is 2 points. So first things first, like, I know this function is continuous, and I should have checked that the previous function is continuous. It's continuous. If I plug in 0, I get 0. Yo, if I plug in 1, that's not enough. Let's plug in 2. 2 is e squared plus 4. Now, like, try to solve this equation. Good luck. That's going to be tough. However, I know, like, 2.7 times itself plus 4 is definitely bigger than pi. I know 0 is less than pi. I got to have an x such that f of x will produce pi. It's the intermediate value theorem. It shows existence. I'm out. Later.